All right. Thank you. Thank you for the introduction, and hello everyone. I'm Daniel from Personae Labs, and I'm going to. So we're going to have two overview sessions, and for this session, I'm going to go through Spartan-ECDSA first, and some of the components in Spartan-ECDSA, we will cover efficient ECDSA and the membership verification. Can you see my screen? I also should
Yes.
share this HackMD quickly. Just shared the HackMD link in the Discord channel, so feel free to check that out. And there are a bunch of links in there, so I think it'll be useful to bookmark it and then refer to the links while going through the circuits.
Daniel,
Mhm.
if you don't mind, since this is a recording that will be watched by others who will follow the fellowship later on, I'll just introduce you very quickly. So Daniel is from Personae Lab. He's the lead dev of the Spartan-ECDSA, and this is our overview session, part 1 of 2 overview session of the audit. Back to you, Daniel.
Thank you. So just to start from the overview of Spartan-ECDSA, I have these slides that I used in previous presentations, so I won't go through all of these slides, but I'll just go over the basics. So Spartan-ECDSA is a library for generating and verifying zero knowledge proofs of membership based on ECDSA signatures, and it provides the fastest proving time in available proof system as far as we know. And to start with the explanation of Spartan, Spartan is a proof system that is a family of non-interactive zero knowledge proofs, NIZKs, and ZK snarks for proving R1CS satisfiability. It works with any of the curve, and it doesn't require any trusted setup. So Spartan-ECDSA is quite obviously based on this proof system. And one key component of Spartan-ECDSA is the SecP and SecQ curve cycle. Recall that ECDSA is based on SecP 256K1 curve, and there is a variant called P256, but Ethereum and Bitcoin, most of the blockchains, use the SecP 256K1 curve. So the curve cycle of SecP, which is SecQ, is a key component in the Spartan-ECDSA, and the curve cycle is the property of two curves that the order of the base field of one curve is the order of the scalar field of another curve. If you're just beginning to learn about Elfman curves, if you're just starting with Elfman curves, this might not make sense, but please don't worry because when writing and reading circuits, these details is not relevant, but I just wanted to explain to just be on the same page. And so this is one component that is important to understand. And yeah, this curve cycle allows us to generate proofs and really quickly and keep the circuit size small. And another optimization that we used in the library is a modified version of the ECDSA verification. I will go through this modification later. And you can also read about this modification in the blog post that is linked in the HackMD. And just to share some concrete numbers, Spartan-ECDSA, the main circuit in the library, which you can use to prove membership to a group of ECDSA public keys, with maximum members of about 1 million. So the tree depth is about 20. The circuit consists of about 8,000 constraints, and you can prove the satisfiability of the circuit using Spartan in about 4 seconds in a browser of a M1 MacBook Pro. And the proof size is about 16 kilobytes, and verification is also succinct. So this is just a basic introduction to Spartan-ECDSA. And I also linked these slides in the HackMD. So if you're interested, feel free to go through all of them. But to go back to the HackMD and to the actual code. So for session 1, I want to go over some of the some of the circom files. But depending on the questions we have in this session, and also the asynchronous communication in Discord, I want to change or modify what we do in session 2, and potentially change the scope depending on how difficult or how hard it could be to understand the circuits and go through all the materials. So please let me know if like some of the resources are too heavy or too requires a knowledge that not many people have. Please let me know. But just to go through the basic files for today. I want to go through these 4 circom circuits. Let me see. Yeah, I think I should just go through all of this. I'm going to explain each circuit and the actual constraints implemented in them in a moment. But before diving deep in each of them, I want to just share how to run the circuits and test the circuits. There's nothing complicated, but one thing to note is that you need to install a version of Circom that is forked. So you need to install this fork of Circom that supports compiling to the base field of SecP256K1, and then you can proceed as you do in normal Circom projects. There are a bunch of jest tests in the repo. So for example, for some SecP arithmetic, elliptic curve arithmetics, there are, I think the coverage is 100%, but I'm not sure. So, but I think with all of these tests, you can go through and run all the circuits. You can modify the tests and run the circuits in a way that you want to. All right, so that's the way to run the circuits and test the circuits. And from here, I'll have to assume some basic knowledge of the curves and ECDSA. But don't worry if you don't understand everything that I explain here. You can go back to the HackMD anytime, and you can ask me anything in the Discord channel. So to explain what efficient ECDSA is, first, to recall standard ECDSA, we have the signing process that consists of these steps, and the verification consists of these steps. I won't go through the exact steps, but just to set the notations here. And if you want to read more about it, if you're new to ECDSA, there's a good explanation, including some example implementations. I linked one resource in the HackMD, so feel free to go take a look. And then, so just to set the notation and recall what standard ECDSA looks like, to go to the ECDSA used in Spartan-ECDSA, which we call efficient ECDSA. The signing of efficient ECDSA is first you simply sign the message hash, the hash of the message, as in standard ECDSA. So the first step is to just go through all these 6 steps and then get the R and S values. And then you compute a group element that we define T. and also compute a group element U. Now we can proceed to generating a proof, a zero knowledge proof, I, that proves this equality. So this is just one scalar multiplication and one group element addition, and check if that equals to the public key that we want to prove membership. And in practice, we also prove that not only we constrain this, but we also prove that the public key is in some set by providing a Merkle proof that this public key is in a certain Merkle tree. So that's another part that I'm going to explain later. But the core part of efficient ECDSA is constraining this thing in the zero knowledge proof. The private input is S, so we don't want to reveal S because S will, by revealing S, we will reveal the public key. So we want to keep the S here private, but we will make TU public inputs. So in the signing or proving of Spartan-ECDSA, the output of sign proof is the proof or the group elements R, T, U, and pi. So with this proof, the verifier can verify that these two equalities hold, and also that the proof that this, the zero knowledge proof that proves that this equality holds is valid, and the public inputs T and U are also valid. Okay. So please feel free to interrupt if you have any questions, or I'll just go to the next section.
Daniel, would the public key be a public input as well?
The public key will be a private input. So yeah, in this example, yeah, good question. In this explanation, there's no mention about which one will be, but in practice, we will provide a Merkle proof in this circuit as well. So we will just check that the leaf of the Merkle proof is equal to this public key, and the Merkle proof is actually valid. So public key should be a private input. All right. So next up is the Merkle tree proof verification, which is not that complicated. This should be the simple part. The circuit is just a clone of a Merkle proof verification circuit from Semaphore. So we just clone that. And the Merkle tree is based on the Poseidon hash function. In the Poseidon hash function, we also implement the constraints ourselves, which I will explain in the next session. But that's just the that's just how the Merkle tree verification works. There's not much special here. Just a standard tree proof verification. All right. So the next part is to explain the SecP group arithmetic, which is required to actually do the ECDSA verification. So in ECDSA verification, you have all these, let's see here, you have all these scalar multiplications and group element additions, and also multiplications of scalar field elements. So we need to have a way to do that in R1CS and CIRCOM. So we implement the arithmetic of SecP in CIRCOM. The arithmetic consists of about 3 operations. We can separate that in 2. One is addition, so simply adding 2 group elements, and the another one is variable-based scalar multiplication. Just say scalar multiplication using the double and add algorithm. So to dive into the addition first. So there are 2 types of additions. One is complete addition and another is incomplete addition. Complete addition takes into account all the edge cases that can occur in of the curve group element additions. For example, the result of adding two group elements might be the point at infinity. And also, let's see, adding same points requires a different formula from than when adding two distinct points. So thinking adding two same points as an edge case, complete addition can take into account all of those edge cases. And incomplete addition is the most like basic version of addition that doesn't take into account edge cases. So if the result is a point at infinity, or if the same if a same point is added, then it won't work. But incomplete addition is a lot simpler to constrain, and complete addition requires more constraints. So we want to use as many incomplete additions as possible in our circuits whenever possible, but we want to make sure that we do complete addition where it's necessary to capture all the edge cases. The actual constraints are inspired by the Planckish constraints from the Halo 2 book. So Planckish is a arithmetization that is different from R1CS, which is usually used in Planck-based, used in various proof systems, but is a extension of the Planck arithmetization. And the Halo 2 book goes really deep into complete and incomplete additions. So I think the book will be a good resource to learn about it if you want to. And then, so this is the first image is the constraints of the incomplete addition. The Planckish constraint can have custom gates, so it can have high degree gates, but R1CS can only have at most degree 2. So we need to modify the Planckish constraints explained in the Halo 2 book to fit into R1CS. So we make that transformation, but the idea, the implementation should be the same. So if when going through the addition constraints in the Spartan-ECDSA circuits, I think it will be useful to refer to the Halo 2 book and its Planckish implementation to get more information on what's going on, and then and also the analysis of the constraints. Right. So those are additions, and the another one is scalar multiplication, which is usually done using the double and add algorithm. And this part, I think, is the most complicated and probably might take time to understand. And if possible, I think it will be okay to just cut this part from the current scope, from the current sprint, current audit sprint. But if you're already familiar with constraining up the curve operations, I think this will be a good exercise, good advanced exercise for you. But so yeah, the circuit we implement is a optimized double and add algorithm, which is also taken from the Halo 2 book. And the optimized double and add algorithm is optimized for constraining the algorithm. So it uses as many incomplete additions as possible. So we analyze the structure, like in short, we analyze the structure of the multiplicative subgroup, and reason that there will be no same points or same x coordinates in like this range of when we index the points in certain ways, so we can do incomplete addition for like this mostly incomplete additions, but for the last like some like rounds, we need to do complete addition. It's something like that. Oops, sorry. And that results in reduction in the number of constraints. So we implement that. But yeah, as I said, it might be quite complicated. So feel free to skip if it seems too hard to take on this in this sprint. All right. So I think that covers all of these things that I wanted to talk today. I think we have more time. So yeah, if you have any questions, feel free to.
Yeah, you guys can ask questions or type it in the chat. I'll read it out. Daniel, I have a question about, so the tree, the membership tree, it's not strictly needed for ECDSA itself. Is it application dependent? Is it because it is something you need for a certain application? Why do you have a tree to begin with?
Great question. So yeah, as you said, it's not dependent on ECDSA, so you can use ECDSA by itself if you want to, but in most of the applications, especially using the modified ECDSA, efficient ECDSA, you want to if you're using efficient ECDSA, you have to do the verifier needs to do a bunch of works outside of the circuit. So the purpose will be to make the public key zero knowledge and also the signature zero knowledge. So if you don't include a Merkle tree proof, there's really no point in like using efficient ECDSA. So if you're using efficient ECDSA, it usually or most of the time, if not all the time, Merkle tree proof verification will come in. And the reason we want to use a tree is to prove membership to a set. So for example, if you own an NFT and someone creates a set, or you create a set, a Merkle tree that contains all of the owners of a certain NFT collection, you can prove that you own one of the NFTs in that collection using efficient ECDSA and a Merkle proof. So basically using Spartan-ECDSA. So yeah, Spartan-ECDSA is basically for those kind of applications. That's why we want a Merkle tree proof. But like strictly speaking, it's not. ECDSA and tree is not related.
Yeah, that makes sense. So the verifier will not actually be verifying the ECDSA itself, because that is kind of like in the pipeline. It is used as a stepping stone to prove membership in, like the public key that is proven membership in a tree has been also proven to sign a correct message to ECDSA.
Exactly, yes.
So you avoid that. Yeah, it makes sense. Another question, like why are the why is the arithmetic not done outside of circuit? Because eventually whatever you do in the arithmetic, it will be it will sort of be verified in the, like one level above in the ECDSA circuit, right? So why is the addition and multiplication outside of circuit?
Outside of the circuit, you mean these things?
Yeah, well, the SecP circuit overall, why do you need it? Because you can think of like all the multiplication, addition, all that as being done outside, but then eventually you have to plug it into the, yeah. So
I think I understood what your question. Okay, so
it's as if if I am, let's think of the ECDSA as verifying that A times B is equal C, for example, something like that for simplicity. I don't care how A and B came about. Like that's the SIGP arithmetic. I don't know how that came about. I just care about the when I plug in all of that into the ECDSA circuit, it computes correctly.
So the circuit that we construct, that we write, is a circuit that verifies that that a correct ECDSA signature was provided. So we encode the verification of the ECDSA algorithm into a circuit, into R1CS. So essentially what we want to do is to check this. By the way, can you see my cursor?
Yeah, yeah.
Just says, yeah, good, great. um, what we want to do is we want to encode this verification into a circuit.
Yeah.
It's S multiplied by T and plus U. And everything in the lowercase is scalar field elements in T. The uppercase ones are group elements. So this is scalar multiplication and this is point addition. So we want to prove that we know S, T, U, and public key that satisfy this constraint without revealing S. So we want to encode this thing into an ROCS. So ECDSA, the proving part is simply done in a cryptocurrency wallet or like any other, or even in like a mobile phone enclave or something. But the verification part, we want to make that journal. So we want to prove that we successfully like generated a signature that passes this verification, and also we know a Merkle tree path that result in a Merkle tree root. So to encode this thing, we need.
So is the computation of T itself, T and U, do they have to be in circuit?
No, the computation in T and U is outside of the circuit.
Okay, yeah, that makes sense.
Yeah, so we do both. Yeah, so we do SECP arithmetic in both inside and outside of the circuit.
Oh yeah, that makes sense. So the SIGP circuit is for basically the final step when we are computing this ST plus U.
Yes, exactly. Yeah.
Yeah, makes sense. Any question, guys? So yeah, the tree and the membership, the good thing is that we are a little bit familiar with it because we had one in the RLN as well. So that should be familiar. You mentioned, Daniel, the standard ECDSA, and is there something that you guys changed in the how ECDSA, vanilla ECDSA is computed? Is there anything that you changed from the standard signing and verification?
So we changed the verification. So essentially, yeah, essentially what we do is we radically change the verification process by including a zero knowledge proof and computing T and U and all those stuff. But the signing, so we change the verification process, but we keep the signing process the same. The reason why is that we want to be compatible with existing wallets, cryptocurrency wallets like MetaMask, and those wallets don't provide a way for third-party developers to access the private key itself. So we can't access the private key of users, so we can't change the signing process. We just have to call the API of for example, MetaMask, and just get the R and S values. So the signing process assumed in Spartan-ECDSA is the standard signing process, but the verification is the part we not change. Yeah, and let's
We do have a question from Lul
Mhm.
T in the chat. He says, was Poseidon 2 considered? He found it while searching for Poseidon, so he's asking about it.
Yeah, we haven't considered Poseidon 2 yet, but I'm not really familiar with the status, and I'm not really familiar with its progress. But yeah, we are sure that we're going to support it when it becomes like going to go mainstream, when it becomes more popular. But the Poseidon hash function we use is the I think it's the version 1 Poseidon.
We talked about this offline, Daniel, about the efficiency gains that you guys had compared to 0xPark's ECDSA implementation. I think you guys went from something like millions of constraint R1CS constraint to 5K, which is like amazing. For those, I think some of the fellows bumped into that old implementation as well. So could you just briefly, in general, speak to what you guys did differently?
Sure. Just a second. Let me just pull up the Spartan-ECDSA repo. Let's see. So So the original Spartan-ECDSA circuits written in Circom, written by the team from Xerox PARC. The verification procedure consists of I'm not sure what this verification consists of. Like, yeah, probably this says 15 million, but like, let's say it's a couple millions to do the same thing as the circuits in Spartan-ECDSA. The reason why the original Spartan-ECDSA circuits requires this many constraints is because they're doing round field arithmetic, which is encoding the signature, the ECDSA signature, and the ECDSA verification procedure. So ECDSA verification consists of many SACP arithmetic. So the circuits encode those operations in the scalar field of the BN254 curve, which has a different prime field, so which operates on a different field, so it has a different order. So for example, you have to split a single, for example, the x coordinates of a SECP group element into, for example, like 4 registers, and have a range check that all of the registers are in the correct range, and do operations on all those registers. So when you want to encode a operation of a different finite field into of a finite field into a different finite field, it requires this like big int operation like thing. So you need a lot of constraints to do that. But in Spartan-ECDSA, we use the curve cycle of SecP called SecQ. So we can directly encode the SecP operations into the circuits without doing any big-end arithmetic. So we can get rid of all of the like splitting into registers and checking the range, get rid of all of them, and just simply do the arithmetic that we need to do. So yeah, that's the main reason we got from like a few million constraints into only like 5,000 constraints.
Amazing.
And yeah. And just to mention another, yeah, and also efficient ECDSA, this transformation computing T and U outside of the circuit also contributes to the reduction in constraints, because the standard ECDSA verification requires 2 scalar multiplications and 2 different scalar field element multiplications. Whereas when you like rearrange the verification equation and pre-compute T and U, you will end up with just this this check, which is just 1 scalar multiplication of what group addition, which is a lot cheaper than doing all this in the circuit. So that's another optimization that we made.
Yeah, makes a lot of sense. Lulti is also asking about ECDSA malleability. Is it something to be considered about here as well?
Yes, great question. So ECDSA, you can generate 2 different signatures, so different RMS for same message. So if you're using Spartan-ECDSA, you should only use it for applications that won't be affected by malleability. So even if a user can generate 2 valid proofs for same message, that will be an issue. So Spartan-ECDSA is not for things like private voting or private coin transfer, of those kind of things that require a thing called nullifier, which requires non-malleability. So this library just provides faster proofing, but does not provide safety against malleability.
So I guess one way would be maybe the proving the uniqueness of the messages, right? Like extra Spartan ECDSA, for example. I could be wrong. I'm just thinking out loud.
Yeah. The sad thing is that there seems to be no way to create a zero knowledge ECDSA proof that is not malleable, because like technically you can create a like simulator that can like generate the same proof, the collection of proof with same distribution. So if unless you have access to private key, it's not possible to it's not possible to generate a non-malleable proof, unfortunately.
Excellent. Yeah, so you gave fellas a lot to go through, Daniel, from now until our next session. We could take a few more questions if you guys have. Otherwise, I'll share the HackMD document and maybe the slide as well, if it's okay with you, Daniel. And
Yeah.
And I think in the next session, probably the questions that pop up in Discord today and tomorrow will inform probably your next session as well, Daniel. So yeah, if there is no more questions, we will pause here and pick it up on Wednesday.
Got it. Amazing.
Okay. Thanks, Daniel. Thanks, everyone. And we will see you on Discord, and we'll see you also on Wednesday for part 2.